Welcome to problems 34 to 39 from Chapter 5. Deshauna and her team gathered data for their ball and recorded it in the table shown at the right. So you can see you have the drop height compared to the rebound height. We're going to answer a couple questions based on this information. What is the rebound ratio for their ball? Well, they've taken 6 different measurements here. So it'll depend on which one you pick as to what that rebound ratio will be, but it should be very similar across the board. So we'll do 124 divided by 150, and 124 divided by 150 is approximately 0.82, and then it's actually 6 repeating, so we'll approximate that to 0.83. We'll just round up to the nearest hundredth. And so no matter which one you use, it should be close to that. On B, it says, predict how high Deshauna's ball will rebound if it is dropped from 275 centimeters. Look at the precision of Deshauna's measurement in the table. Round your calculation to a reasonable number of decimal places. So if we know the drop height is 275, what will be that rebound height? So we'll have to figure out what the x is, and that's equal to, and approximately our rebound ratio from above was 0.83. So then that means we need to solve this equation, multiply both sides by 275, and we're going to get a rebound height of approximately, 228.25. 228.25, and we can round that to the nearest whole number, so we're going to say approximately the rebound height is going to be 228 centimeters. And the reason we went to 228 is because look at all the rebound heights. None of these went to the nearest tenth or hundredth, so that's why we went ahead and rounded it to the nearest centimeter. Part C, suppose the ball is dropped and you notice that its rebound height is 60 centimeters. From what height was the ball dropped? Use an appropriate precision for your answer. So now on this one, we know the rebound height is 60. So 60 will now be our top number because we're doing the rebound height divided by the drop height. So we don't know what the drop height is. That's what we need to find out. But we also continue to know that that rebound ratio is approximately 0.83. So we're going to solve this one the same way that we solved B, except now we're going to multiply both sides by x. And by doing that, that doesn't solve the problem in one step because that just gets the x out of the denominator. Now we can go ahead and divide by 0.83, and we're going to get x is equal to 60 divided by 0.83 is 72.289. It actually just keeps going, so this is approximately, because we want everything rounded in the nearest centimeter, 72 centimeters. Next, D, suppose the ball is dropped from a window 200 meters up the Empire State Building. What would you predict the rebound height to be after the first bounce? So we did go from centimeters to meters, but as long as the ratio still stays the same as 0.83, we should be okay. So now we know, we don't know the rebound height, but we do know the drop height. So we got x divided by 200 is going to be equal to the 0.83. So we'll solve it the same way that we actually solved B, is multiply both sides by 200, and that will get x by itself. So 200 times 0.83 will be 166. So we believe that it will rebound approximately 166 meters. So just because we changed the units from centimeters to meters, that rebound ratio should still remain the same. And on E, it says, how high would the ball in part D rebound after the second bounce, after the third bounce? So if we continue this on part E and say, okay, well now it's at a height of 166. So that's our new drop height. What is the rebound height going to be? Once again, approximately the rebound ratio of 0.83. So we will now multiply both sides by 166, and x is equal to 166 times 0.83, which is approximately 137.78, and we will approximate that to 138 meters again, so 138 meters. And so we'll do it one more time. It wants the third bounce also, so this is the second bounce. And we'll do it again. The 138 is the drop height. We got x as our rebound height. So we're going to solve it exactly the same way each time here. And this time we're going to multiply by 138. And we have x is equal to 138 times 0.83. And we get 114.54. So that's approximately 115 meters. And this will be 115 meters on the third bounce. And so I think we've answered all the questions. Once again, how high would the ball in Part D rebound after the second bounce? We got 138 meters. And then after the third bounce, I got 115 meters. Question 35. Look back at the data given in problem 5-18 that describes the rebound ratio for an official tennis ball. Suppose you drop such a tennis ball from an initial height of 10 feet. And then we're going to answer a couple of questions based on that. So looking back on 5-18, it says tennis balls must rebound approximately 111 centimeters. So 111, that's the rebound height, when dropped from 200 centimeters. So if we divide that, we get a rebound ratio of 0.555. So to be able to answer part A, if the initial height is 10, then what would be the rebound height if you dropped it? So we can multiply both sides by 10, and we get x is equal to 5.55. Now this is in feet, so that's 5.55 feet after one bounce. And then on B, it wants to know after the second bounce. So now we have a new height of 5.55, so x divided by the new height, 5.55, is equal to this ratio of 0.55. And if we multiply both sides by 5.55, lots of fives, we get x is equal to 0.55 times 5.55 is approximately, it's 3.08025, but we're going to approximate that to 3 feet after the second bounce. And then we will do a couple more times, and then we have the fifth bounce that we're looking at. And so instead of just keep going here and have to, figure out the third, then the fourth, then the fifth, we're going to use what we learned earlier, and if the rebound height is the fifth bounce, we're now going to take the initial height, which was 10, and multiply that by 0.555, which is that rebound ratio raised to the fifth power, since we're looking for the fifth bounce. And so if we do that, we get approximately 0.527. So that'll be 0.527 feet after the fifth bounce. And now, obviously, we could have done the same thing for A and B, but just showing you after a time, as to that rebound ratio just keeps getting multiplied by the initial height that the ball was let go. 36. Solve the following systems of the equations algebraically and then confirm your solutions by graphing. So, still solving systems. First one is set up for substitution. We're going to substitute 3x minus 2n for y into the second equation. We will then distribute the 2. Combine your like terms. I'm also going to add the 4 to the other side. Divide by 10. x is equal to 1. We'll go ahead and plug that back in the first equation. Y is equal to 3 times 1 minus 2. 3 minus 2 is 1. So we have an ordered pair of 1, 1. We're going to go ahead and verify that over here on the graph. We can graph the first equation using slope and y-intercept. So y-intercept is negative 2 and a slope of 3. So that's 3 over 1, rise over run, up 3 over 1. We can do that a couple times. We can go backwards, down 3 to the left 1, and then use a straight edge. And there's your first one. And then I'm going to take you the second equation, which was 4x plus 2y. I'll do that down here. 4x plus 2y equals 6, and write it in slope-intercept form by subtracting the 4x. 2y equals negative 4x plus 6. Divide by 2, and I get y equals negative 2x plus 6. So we have a slope of negative 2 and a y-intercept of 0, 6. So I'm going to go up to 0, 6. That's my y-intercept, and then down 2 over 1. Down 2 over 1. Oh, whoops. I see what I did. That's not right. Let's go back here. I didn't divide the 6 by the 2. So 6 divided by 2 is 3. So now the slope is negative 2 and the y-intercept is 3. Let's try that again. It wasn't going to work, so I knew I made a mistake. So there's 0, 3. Now down 2 over 1. Now intersects at 1, 1. And so I get a couple more points there. Use a straight edge. And so that represents the solution 1, 1, which is what I found algebraically. B, once again, it is set up for substitution. X is equal to y minus 4. So 2 times y minus 4 minus y equals negative 5. Distribute. Combine your like terms. 2y minus y is y. I'm also going to add the 8. So that looks like we get y is equal to 3. Plug it into your first equation. 3 minus 4 is negative 1. So the ordered pair is negative 1, 3. And that's for part B. So we'll graph both of those once again. Take this equation and solve it for y by adding 4 to the other side. So that gives me y is equal to x plus 4. Slope of 1, y-intercept of 4. So up here, I'll do it in red this time so we can see the difference in the two. So 0, 4, and then up 1 over 1, or down 1 to the left 1. Use that straight edge. And then on the second equation, I'm going to add y to the other side and get 2x equals y minus 5, and then add 5 to the left side. So I get y is equal to 2x plus 5. So a slope of 2, a y-intercept of 5. And so on this one, I go up 2 over 1. That's getting farther away from the line, or down 2 to the left 1. And you can see that it will intersect at this point right here at negative 1, 3. So we did check our solutions by graphing. Question 37. Lona received a stamp collection from her grandmother. The collection is in a leather book and currently has 120 stamps. Lona joined a stamp club which sends her 12 new stamps each month. The stamp book holds a maximum of 500 stamps. Complete the table below. So she will get 12 new stamps each month. So month and the number of stamps. She started with 120. After the first month, she's at 132. After the second month, I'm just going to add 12 new stamps each time. And so that's 144, 156, 168, and 180. And we could, keep going. Obviously, it holds a maximum of 500 stamps, so it can go for a while. But, what are we looking at here? How many stamps will Lona have after 1 year from now? And 1 year is 12 months. So we could continue the equation out for a little bit longer. But look, every month she's gaining 12 new stamps. She starts with her initial value of 120 at time 0. the rate of change is 12 stamps. So we could think of our equation for B as to y is equal to 12 new stamps each month plus the starting value of 120. So after 12 months, 12 times 12 plus the original 120, you're going to have 144 new stamps. And if you add the 120 that she got from her grandmother, that's going to be 264 stamps. So on part B, how many stamps will she have? She'll have 264 total stamps. Alright, on part C, it says write an equation using function notation to represent the total number of stamps that Lona has in her collection after n months. Let the total be represented by T of n. So on C, I already kind of wrote an equation to help out with part B, but it wants us to write it in function form using T of n. So T of n is equal to, still going to be the same thing, 12 times n plus 120. So T of n is equal to 12n plus 120. And then on D, solve your equation from part C for n when T of n is 500. That's the total number of stamps. So how long will it take her basically to fill up her book? Will Lona be able to fill her book exactly with no stamps remaining? How do you know? And when will the book be filled? So we have a couple questions we're trying to answer here. So we know the output is 500 maximum. So that's where we're going to set the T of n equal to 500. And then we're going to solve this equation, subtract 120. So we get 380 is equal to 12n. Divide by 12, and does it come out exactly, or do we have a remainder? So 380 divided by 12 is 31 2/3. So you can see that will Lona be able to fill her book exactly with no stamps remaining? She will not. And then how do you know that? Because it doesn't go, when we go to solve for n, we're going to need 31 2/3 of a month to do that. And then will the book be filled at that time? Or no, when will the book be filled? So you can't have 31 2/3 of a month, so it's going to take 32 months to fill the book, and then she'll just have some leftovers for a new book. So just make sure you answer all those questions from part D. And you can see I did below where she will not be able to fill up her book exactly because 380, which is where I took 500 minus the 120 she initially had, is not a multiple of 12. And then the book will be filled after 32 months, or when she hits 32 months, because at 31 2/3 is when it would be filled, but you're not going to have that 2/3 of a month. So you got to go up to 32 months. Use slope to determine whether the points A, B, and C are on the same line. Justify your conclusion algebraically. So what we're going to be looking at is if we can look at the slopes of the lines, then we can determine if they are on the same line. So let's start with AB. So we're going to look at the slope between the points A and B. And then that will be the change of y. I'll do 6 minus 5 over the change of x, negative 2 minus 3, and that will be 1 over negative 5, or it's equal to negative 1/5. We'll now look at the slopes from A and B to B and C, and that is equal to 7 minus 6 and negative 5 minus negative 2, and that's 1 over negative 3, or negative 1/3. So if the slopes for A and B is negative 1/5, and then the slope for B and C is negative 1/3, then they all can't fall on the same line because they have different slopes. And so I said they are not on the same line because these slopes are different. Another way that you could potentially look at this is, I didn't have a graph on here, but you could also graph this and look at the slope triangles between the 3 points. And you would also see that those are different as well. So just another way that you could potentially look at it. 39. Serena wanted to examine the graphs of the equations below on her graphing calculator. Rewrite each of the equations in y form when the graph is solved for y so that she can enter them into the calculator. Now, you guys might not have the calculator to do that. You can use the Desmos tool to plug these in if you've done that before, but I'll just do it on my graph here so that you can see what they look like. So on 39a, we have 5 minus, I'm going to go ahead and distribute the negative, minus y plus 2 equals 3x. I'm going to solve for y, so this will give me negative y, combine the 5 and the 2, subtract the 7, and I don't have y solved for, I have negative y solved for, so I need to divide everything through by negative 1. So y is equal to negative 3x plus 7. So I can graph this on here. We got the y-intercept, and then the slope is down 3 to the right 1, or you can go up 3 and to the left 1. And so then you can use your straight edge to graph this, and that's the equation y equals negative 3x plus 7. And then on B, if I distribute the 5, that's 5x plus 5y equals negative 2. Subtract the 5x to both sides. You get 5y equals negative 5x minus 2. Divide by 5. And we get y equals negative x minus 2/5. Now, because your y-intercept on this one is not necessarily the best in terms of being able to graph it, that's part of the reason why they're saying use the calculator. We're going to look at this one a little different. Maybe we can pick some numbers that would work, maybe some nice values that we can get to work, and if not, we can just kind of approximate, what it is and what we're looking at. So y is equal to negative x minus 2/5. And now that I reread the problem, I guess it doesn't say that we have to graph. It says rewrite each of the equations in y form so that she can enter them into the calculator. So I guess I'm done. Here's equation A, and here's equation B. So if you want, I guess you could plug them in there and see what happens. But now that I reread the question, it only wants us to rewrite them in y equals mx plus b form.